Hello, Luke. Welcome to lesson 97. So today we're going to be talking about geometry, and in particular we're going to be talking about the Pythagorean theorem, which is a very, very important theorem, one you've probably heard of before, but we haven't talked about it for a long while. And if you haven't heard about it, that's fine. You will today. So let's get started. We're going to begin our conversation today by talking about angles. All right, so angles should be review. We could go all the way back, I don't know what it was, lesson 5 or something like that, when we talked about angles. And I believe you even had a study sheet in which you memorized some of the different aspects of angles. So really quickly, without spending a lot of time, let's try to remember what an angle is. And there are multiple definitions out there, but basically the way we're going to describe it is that an angle has kind of a corner or a vertex, maybe a beginning point, in which two rays extend from that point, right? So here we have our vertex, our beginning point, and then obviously we have the two rays. One kind of going here, and then the other one going up, right? And when we think about angles, we like to measure kind of the distance between those two rays, all right? So if we kind of draw a little arc here, the measurement, the distance between these two rays is important for a number of reasons in geometry. And so we give this a special unit. We call them degrees, right? It's the number of degrees between the angles. And remember, the notation for that is this little circle, all right? So the degrees here might measure, I don't know, maybe it's 50 degrees, okay? And remember what that means again. So it's just measuring from here to here. We're going to call that 50 degrees. Now, we could get a protractor and measure this exactly. I'm guessing when I say that 50 degrees. But there are ways that you can measure this accurately and verify the accurate degrees here. So this one we're going to call it 50 degrees. And that forms an angle, right? And the angle in this case, remember we talked about these? This would be called an acute angle, all right, because it's less than 90 degrees. It's acute. It's acute angle, less than 90 degrees. All right, now this next angle, it's in a little bit of a different orientation, but the same process applies. We're measuring the distance between these two, and this one is actually greater than 90 degrees. And how do I know that? Well, if I think about it, a 90 degree is this one down here. A 90 degree is going to form a box in the corner, and it's actually going to be a square. All right, there should be this perfect square in the corner, and the two sides of the angle go up one side of the square and then across the bottom of the other side of the square. Okay, and if I go back to this acute angle, clearly I could not draw a square in here, right? Because a square would look something like this, and it would go, over our angled line. So clearly that's not a 90 degree angle. This one, you might say I almost could draw a square, but if I kind of, make a perfect square here, which is obviously hard to do freehand, but this is going to be kind of the square, something like this, right? And you can see how the problem here is that this line isn't straight enough, right? It's too large. The opening here is too large for this square to fit in. This side is not going up the side of the square. It's going kind of away from the square. So this is greater than 90 degrees. You might say, the side of the square, this is going to be at the 90 degree mark, and that should be a straight line. But this angle is larger than that. So do you remember what it's called? We give this one a name. Just like we have the acute over here, do you remember what this one's called? This one's called the obtuse. The obtuse angle, meaning that it's greater than 90 degrees. Okay? And the acute is less than 90 degrees. Okay? All right, and then we already kind of touched on it, but this one here is our 90 degree angle, and we give that one a special name. We call it a right angle. Okay? This is all review. So hopefully there's nothing new here and you knew all of this already. So let's move on. The next topic here, we're going to take angles, and now we're going to start connecting some angles together, and we're going to create triangles. Okay? So a triangle is just a shape that has three angles, and all of the lines from those angles connect to each other. And we can get, all kinds of triangles, big and small and flat and all kinds of different kinds. All right, and when we talk about triangles and angles, all right, an interesting thing shows up. So, and actually this one is a 90-degree angle here, so we can draw a box. This will be an arc. It's not a 90 degree. These are not 90 degrees. This is not, but this is. And this is not. So when we talk about triangles and the degrees for their corners, you might say, a very interesting thing turns up, and that is that all three angles will always sum to 180 degrees. All right, so this looks like kind of an equilateral triangle, right? So as such, each of these angles are going to be the same, and we know that they're all going to be equal to 180 degrees. And actually, I don't know, this, it might not. We're going to pretend it's an equilateral triangle. I actually think it's a little bit off. But if they're all the same degrees, we're going to have 60 degrees here, 60 degrees here, and 60 degrees here. All right? And if you add those up, they sum, I'm just going to say 60 times 3, since there's 3 of them, they sum to 180 degrees. And that is true for every triangle. So we know that this one here is 90 degrees in the corner. We don't know what this side angle is or this top angle, but we do know that, angle, we'll call this angle A, this angle B. We know that A plus B is going to have to be 90. And how do I know that? Because I know this one is 90, and I know that all three of them have to add up to be 180 degrees. So that would mean 180 minus this 90 is 90 left over. So this A plus this B, they have to equal 90 degrees. Okay? So it's a very useful rule to remember, a useful theorem to remember. They'll always add up to 90 degrees. Same thing would apply to this one. They're going to add up to 90 degrees. And I can get as wild as I want with my triangles, and those angles are still going to add up to 180 degrees. Okay? All right, moving on. Let's talk about a specific triangle. We're going to talk about right triangles. Now, what's a right triangle? Very simple. It's a triangle that has a 90 degree in it. All right? If it doesn't have a 90 degree in it, it is not a right triangle. So if I have this one, for example, this one is not a right triangle, because if you look at all the corners, this corner is not a 90 degree. This one's not a 90 degree, and this one is close, actually, now that I'm looking at it, but no, it's still not quite a 90 degree. So therefore, it's not a right triangle. Okay? All right. So when we talk about right triangles, we can now associate a very important theorem with right triangles, and that's the Pythagorean theorem. That's what we're trying to get to in this lesson today. And remember, this only applies to right triangles. All other triangles, it won't work. Okay? So that's really the first thing you need to verify before you use this theorem, is that the triangle that you're looking at is indeed a right triangle. All right? So when we talk about right triangles, before we get into the theorem here, let's just do a little labeling. First off, when we look at a right triangle, we better find our corner, because that's the 90 degree. And if it's a right triangle, it has to have it. All right? So just kind of pick that out on the triangle. All right? And then what we're going to do is we're going to call one side of the triangle that is part of the angle for that 90 degree, we'll call that side A. And then we'll call the other side of that 90 degree angle B. And that's the order that that's the notation we're always going to use. Now, in practice, it doesn't matter which side is A and which side is B, as long as it's part of this 90 degree. So if I wanted to, I could, call this one B and call this one A. That's fine too. The important thing is that the two lines that are composing the 90 degree angle have to be called A and B. All right? So that's just some notation. Now, what is the third side going to be called? Well, we're going to call that line C. Okay? Now, its official name is the hypotenuse. the hypotenuse. All right. So this side, the side that is opposite of the 90 degree, that is the hypotenuse side of the triangle. And we call it side C. All right. Now this, again, is so important. Make sure that you're writing this down in your class notebook because you will need to remember this later on. Very important. All right. Now, once we have all of our sides labeled in our triangle and we know what side is which, we can now start to look at this Pythagorean theorem and actually use it. All right, so what is the Pythagorean theorem? Well, it says that given C is the length of the hypotenuse, this is all what we've just been saying, C is equal to the hypotenuse, and A and B are the lengths of the other sides, A and B, other sides, then, here's the important part, A squared plus B squared equals C squared. All right? Now you might say, what in the world? Who thought this up? Well, it was Pythagoras, and what he recognized was that if you take a square, ooh, now this is going to be hard to do actually. All right, so that looks pretty good. So if I take one side of this triangle, this side here, and I turn that side into a square. Now, I don't know how perfect my line actually is. It doesn't quite look like a square, it looks more like a rectangle. So you'll have to bear with me here and just pretend that this side, we're going to call it side, well, yeah, we'll call it side A. This A length is the same length as this side and the same length as this side and the same length as this side. So this is a square made up of one side of this triangle. All right, and then if I take another square, I take this other side, we're going to call it the B side, and we make another square with that length off of that side of the triangle. And then finally, you've probably guessed it, we will then take a third square that's based on the length of the hypotenuse. All right, so there is our final square, and his length is equal to that, the hypotenuse side, so we'll call it C. So all these are the same. So you can see what we've done here is we said, okay, this is our right angle here. And so this side is A, this side is B, this side is C. And we've basically created these three squares based on the lengths of these three sides of the triangle. Now what's interesting, and this is what Pythagoras proved, was that if you take the area of this orange square, which again, I apologize, it doesn't look too much like a square. You'll have to use your imagination. It's more of a rectangle, but pretend it's a square. So you have the area of that square, whatever that is, and if you add it to the area of this square, whatever this is, lo and behold, that it will equal the area of this square. This large one from the hypotenuse. And that'll be true for any and all right triangles. It's amazing. Absolutely amazing. So that is what's going on behind this formula. That's why it's A squared, because how do you find the area of a square? You square the sides. A squared plus B squared, that'd be the area of this square, equals C squared, the area of this. All right, now we won't go into the proof behind all this. You'll just have to take my word for it, take Pythagoras' word for it, that actually it does turn out for every right triangle. All right, but this is hugely beneficial because now what we can do is we can take triangles that are right triangles, and again, they have to be right triangles, and if they give us, a couple of lengths here, let's say they say, let's say this one is 3, well, no, we'll say this is 3 units, this is 4 units. What's this unit here? I mean, how long is this line? All right, and to know that, we use the Pythagorean theorem. So we first find the right triangle side, the right corner, okay, the right angle, excuse me, and then we're going to say, okay, where's our A's and where's our B's? So if this is the corner, then this could be A, this could be B. And what does the formula tell us? A squared plus B squared has to equal C squared. So now we can start plugging things in. The A is a 3. So that's 3 squared, plus the b, which is a 4. That's 4 squared, equals c squared. Now we just do some simplification here. We have 9 plus 16 equals c squared. And then if we add these up, we end up with 25 is equal to c squared. Now, how do we solve this? Well, it's an equation that has perfect squares on it, right? So one way to think about it, there's multiple ways to think about it, but maybe just to kind of review a previous lesson, we could take the square root of this side, and that's going to give us c. The square root of this side is going to give us a 5, but it's actually going to give us a plus or minus 5, right? But here's where you have to take the context of the problem into your thoughts. So here we have c is equal to either a plus or minus 5. Would it make sense to say that the length of this side is a minus 5, a negative 5? Absolutely not. That does not make sense because we're talking about length here. You can't have something that's negative 5 units long. All right. So therefore, that answer just simply doesn't make sense. So we can just select the positive answer and say that c has to be equal to 5. All right. So that is the length of c. It's 5. Okay? Pretty straightforward. Okay, let's try a couple more here and just see how you do. Let's say I have, let's say the length on this side is 5. The length on this side is 12. Can you find this side for me? And I'm not going to tell you what it is. I'll just call it side S. Can you find, well, that looks like a 5. Let's just call it X. Side X. All right. Can you find the length of that side based on or using the Pythagorean theorem? Go ahead and pause the video and try it out and see how you do. All right, so let's see how you did here. So once again, the first step is always to find that right angle within the right triangle. That's so important. So we find it. It's not this one. It's not this one. It's this one. This is the right triangle. And this triangle is in kind of a strange orientation. But you can see how this still does make a box in this corner, a perfect square. Okay, so that is the right triangle. That would mean that, you know, the two sides touching that, it doesn't matter which we call it, but this could be an A and this could be a B. All right, could be either, it could be the other way around. This could be a B and this could be an A, it doesn't matter. Okay, so now once we have that labeled, then we know that this side is our hypotenuse. So X is the hypotenuse, which means that X is actually the C. Okay, and then we can work out our formula. So our formula says a squared plus b squared equals c squared, and we can plug things in. We have 12 squared plus 5 squared equals c squared. This is going to be 144 plus 25 is equal to c squared. And if we add those up, we end up with 169 equals c squared. Now if we square root both sides, kind of a tricky one here, but that's actually 13. And again, we're going to choose the positive 13 because negative doesn't make sense. And therefore we know that c is equal to 13. All right? It's as simple as that. Now, let's try another one here. This time, let's say I give you, this one is 12. Well, we'll make it a little simpler. Let's make it 15. And then we'll say this side is 12, and this side is the question mark. All right, so pause the video, see if you can handle this one. All right, so what do? Well, we start by finding the right corner. So where's our 90 degree? Here it is, right? And that means this side we're going to call A. The X side we'll call B. Okay, so in this case it's not the hypotenuse that we're trying to find, it's actually the B. And then this is our C, the hypotenuse. So what's our formula? Our formula is a squared plus b squared equals c squared. What's the a squared? Well, that's the 12, so we can plug that in. The b, well, that's the x, so we don't know what that is. I'll keep it as the x since that's what it is in the problem. We don't know what that is. That's an unknown. C squared, we know that. That's 15. All right. So now we've got some work here that we can do. So 12 squared is 144. plus x squared equals 225. And now we can solve by subtracting our 144 from both sides. And that's going to give us x squared is equal to 81. And then if we take the square root of both sides, we end up with x is equal to plus or minus 9. But we're going to go with 9 since we're dealing with length. So what is b? B or x maybe? X is equal to 9 units. Whatever those units are. Inches, feet, yards. It doesn't say in the problem, so we'll just leave it like this. All right? Very good. Excellent. So if you can handle those, the rest of them should be pretty simple. You're just doing the same thing over and over again. Maybe we'll do one more though. Yeah, let's maybe just do one more that's not quite as nice as the ones that I gave you. So let's say we have our triangle, and we'll say that we have I'm pulling this actually right from the book. We'll call it 12 and 8. Okay, and they want you to solve for m, find m. So once again, we need to find our corner, so we make sure we have all our sides labeled correctly. We'll call this side A, this side B. And then we have a squared, well that's 12 squared, plus b squared, well that's 8 squared, equals c squared, well that's m squared. And then if we do the math here, we end up with 144 is equal to plus 64. And if we add those up, we get, what do we get here? 208 is equal to m squared. And once again, we do the square root trick here to end up with m is equal to the square root of 208, but we should really try to take that 208 and simplify it. So if we break it down into its prime factors, what do we end up with here? Lots of 2's, and a 13 is prime. So we can pair up some 2's. These 2's will come out from the square root as a 2. This pair of 2's will come out of the square root as a 2. And then we have left inside the square root the 13 and of course the 1. So 13 times 1 is 13. And then this can simplify to 4 times the square root of 13. So that would be our simplified version. So it doesn't come out as nice as the other ones, but it's still an appropriate number. M is equal to 4 times the square root of 13 units, whatever units they happen to be. All right? Very good. So we will stop here. Good luck with your seat work, and I will see you tomorrow.